Okay, this is a RLC natural response, and it's going to be underdamped. But you're not supposed to know that right now. It's kind of a secret, but that's what it's going to be. So there's our cap and our inductor, and there's our resistor. So this is a variable resistor. That is, they want us to solve for it. So they're drawing a variable resistor symbol in there. So this is our voltage signal. We have these I of R, I of L, I of C, all leaving node A. We've got a 10 millihenry inductor in here. We've got a 1 microfarad cap. We're given that the initial voltage is V0 across all three of these guys is 10 volts. And the initial current is big I sub 0 is 80 milliamps through the inductor. And the other thing that you're given on this guy is that you're given the roots. S1 is minus 8,000 plus J 6,000 radians per second. And S2 is minus 8,000 minus J 6,000 radians per second. So the thing to realize is that this thing here without the minus sign is alpha. So alpha is 8,000. And this thing here is omega D. So omega D is 6,000. And the other thing is that these are complex conjugates. S1 and S2 are complex conjugates. Therefore, this thing is underdamped. So that's how you know that it's underdamped, is by looking at these roots. They want us to find R. Part A is find R. What is the value of R that will produce these roots? And what is V prime at 0? What is the rate of change of the voltage at 0? What are the B's? So this is a hint that this is going to be a underdamped system, because B is the letter used for the coefficients in our general solution. And then the last thing they want us to find is the current through the inductor as a function of time, IL of t. So the first thing we can find is R by realizing that we could use this formula alpha equals 1 over 2 RC. We're given alpha, it's 8,000. We're given C, it's 10 millihenry. So the only unknown in there is R. So 8,000, which is alpha, equals 1 over 2R, and the cap, 1 times 10 to the minus 6 is our cap. So R falls out to be 62.5 ohms. So that's our first answer. Right? Part B, they're asking what is V prime at 0? So we have a couple of tricks that we use on these problems. If you look at the review sheet, the summary sheet, there's a page on there that has several tricks. One is KCL at A, add up these three currents at A. The other one is I equals CV prime. So that relates V prime, in this case, to the capacitance and the current through the capacitance. And the other one is Ohm's law through here. So we're going to use those in different sequences for this problem. There's kind of two halves to this problem. So we're trying to find V prime at 0. So we're going to use IA sub C equals CV prime. So we need I sub C, right? And we can get I sub C if we used KCL at node A. If we had the other two currents, so then we would need I sub L and I sub R. So I think I kind of mixed that up a little bit, but it'll be fine. So first thing is use Ohm's law. So I sub r at 0 is going to be, V at 0 over R, right? The current through this guy is just the voltage, initial voltage across it over its resistance. So it's going to be 10 over 62.5. It's going to be 160 milliamps. Then we can use KCL at A, and we can get I mixed up. Yeah, it's fine. So so I sub C at 0 is just going to be minus I sub L at 0 minus I sub R at 0. Okay, this is just KCL solved for I sub C at 0. Okay, so this is minus 80 because this is given. I sub L at 0 is the same as capital I at 0. It's 80. Okay, and the minus sign comes from, these are three positive signals summed at A, and then solving for I sub C, you get the two negative signs. And likewise for the 160, which we just solved for I sub R. So this is minus 240 milliamps. That gives us, we have, we're trying to get I sub C. So we need I sub L and I sub R, but we're given I sub L, and we solve for I sub R. So that's, sorry about the confusion there. But anyway, you get I sub C at 0 is 240, and then you can go back to this I equals CV prime thing. So I sub C at 0 is just CV prime at 0. So V prime at 0 is just, 240 over 1 times 10 to the minus 6. It's just solving this guy for V prime at 0. Put the C on the bottom. And this is minus 240 kilovolt seconds. That's an answer. All right, that was part B. Okay, for part C, they're asking for IL of t. So this part is kind of long. We're going to solve for V of t, and then we're going to solve for I sub R of t using Ohm's law. Then we'll take the derivative of V, multiply times C, and that'll give us I sub C of t. And then KCL, we'll take the difference of these two guys, I sub R and I sub C, and we'll get I sub L. So that's what we're going to do. So first we need the general solution V of t, because we just need that. So we're going to use the underdamped EQs toolkit. So we have two equations that they give us. V at 0 is B1, and V prime at 0 is minus alpha B1 plus omega D B2. This comes from this is our toolkit, I call it. So B1 is V at 0, that's given, that's 10 volts. This capital V at 0 is the same as V sub t, at 0, or V of 0. So this is just 10 volts, so that's B1. That's one of our B's. And the second guy, turns out we have everything here. So it's we have alpha, that's minus 8,000. We just got B1, there it's 10. We have omega D, it's 6,000. And the only unknown is B2, but we even know V prime at 0. We solve for that right here, right? This is minus 240 thousand. So the only unknown in this thing here is B2. So therefore, solving for B2, we get minus 26.7 volts. It's B2. So there's our B's, B1 and B2. That was part C. Okay, we're going to need V of t later. So I'm going to go ahead and just get that now because we have our B's and our alphas and everything. So also from the toolkit is this thing. V of t is B1 cosine omega dt plus B2 sine omega dt times e to the minus alpha t. We have all of these things. So V of t is 10 cosine 6,000 t plus, minus 26.7 sine 6,000 t e to the minus 8,000 t. Okay, we're going to need that. All right, so that was a bunch of stuff. We're going to part D. We need I sub L at t. So we're going to use KCL at A. We're going to use I equals V over R, I sub R equals V over R, and we're going to use I sub C equals CV prime. Our three tricks. So KCL at A tells us that I sub C I sub L, the thing that we need, the thing that we're asked to find, I sub L, is minus I sub C minus I sub R. So we need I sub C and I sub R as functions of time, because we're trying to find I sub L as a function of time. So we need I sub C as a function of time and I sub R as a function of time. So Ohm's law will give us I sub R as a function of time. So I sub R of t is just V of t over R. All right, so it's just take this V of t that we just got and divide through by 62.5, which is our resistance. So this guy is going to be just taking this guy and dividing through by 62.5. You're going to end up with 160 cosine 6,000 t minus 426 sine 6,000 t e to the minus 8,000 t, and this will be milliamps. So that was I sub R. Now we need I sub C on our way to getting I sub L. Okay, we can get I sub C by this I sub C equals CV prime thing. We have the value of the capacitance C. We just need V prime. Okay, so we're going to take a bunch of derivatives here. So it'd be good on your homework to write down the rules that you're using. I'm going to do that here because I can't remember a lot of these derivative rules half the time. So if the derivative of a cosine, a function of cosine u, where u is also a function of t, so or x. Here it's t. So derivative of cosine u is minus u prime sine u. The derivative of sine u, where u is a function of t, is u prime cosine u. The derivative of two functions of time, uv, is uv prime plus vu prime. And the derivative of e to the u, where u is a function of t, is u prime e to the u. So these are the rules that we're going to be using to do this guy right here. So we need v prime. So I'm just going to rewrite v so that it's on the same page here. So v function of time, I'm just going to leave out the t because it's messy. 10 cosine 6,000 t minus 26.7 sine 6,000 t, the whole thing times e to the minus 8,000 t. That's v of t. It has units of volts. So v prime is going to be, take the derivative of the e thing first, it's going to be minus 8,000 e to the minus 8,000 t. That's a derivative of e to the minus 8,000 t times the same thing, right? We're doing this uv prime v prime thing. So now it's just same trig stuff. 10 cosine 6,000 t minus 26.7 sine 6,000 t plus, okay, the e stuff, e to the minus 8,000 t times the derivative of the trig stuff. So this is going to be the derivative of cosine u is u minus u prime. Sine u is going to be minus 6,000 10 cosine 6,000 t sine. This is sine. Minus 6,000 26.7 cosine 6,000 t. It's the derivative of this thing here and the derivative of this thing here. Okay, then multiplying the 8,000 into this top line, you get let's see, just copying, yeah, multiplying this 8,000 thing, you get e to the minus 8,000 t. That's just this thing here, bringing that down, and then multiplying 8,000 across here, you get minus 80,000 cosine 6,000 t plus 21,000 or 213,600 sine 6,000 t. Pulling the negative sign out of this thing, you get, and then factoring out the e to the minus 8,000 t, you get minus 60,000 sine 6,000 t minus 160 200 cosine 6,000 t. Let's see. Yeah, then we've got 2 cosines and 2 sines. We can collect those things, and you end up with, let's see, oh man. Extra parenthesis on there. $153,600 sine 6,000 t minus 240,200 cosine 6,000 t. That's just collecting the 80,000 and the 160. Those are negative adding, so that ends up with negative 240,200, and then the 213 plus 60. Or minus 60. The 213 minus 60 ends up with 153,600. Anyway, this is v prime. All of these are v prime. That was just taking the derivative of v, which is calculus stuff. I'm pretty rusty on that. But anyway, that was the derivative of v. All right, once you have that, then I sub c equals cv prime. So it's just the capacitance, 1 times 10 to the minus 6 times v prime. So it's just multiply this dude by 1 times 10 to the minus 6, and you end up with e to the minus 8,000 t, 154 sine 6,000 t minus 240 cosine 6,000 t, and that ends up being milliamps. And we can do what we're trying to do, which is IL we're using KCL way back in here. IL is minus I sub C minus I sub R. So here's I sub, where is it? This is I sub C, this guy. This is I sub C. This is I sub R. So we've got, what are we doing? We're subtracting the negative this and that. You got to keep track of your negative signs. It ends up, it's easy to mess up, but it ends up being e to the minus 8,000 t 272 sine 6,000 t plus 80 cosine 6,000 t milliamps. I'm just taking this this 240 and this 160, combining those, and then combining the 425 and the 154, keeping track of the signs because we're subtracting, or they're, you know, negative. Yeah, anyway, keep track of that. Yeah, shoot, that's our answer, right? So what does that look like? It's going to have this e to the minus 8,000 t envelope, and at 0 it's just going to be 80 because sine of 0 is 0, and cosine of 0 is 1, so it's just going to be 80. And I'm not saying I know. I mean, I had to graph this in my calculator, but it's going to be 80. Whether it goes up or down, it's hard to tell, you know. But it turns out that it went like this. Yeah. And it kind of decays down to 0. So this is I sub L of t. So that was that. Sorry about the messy derivation here. I'm sure you guys can all do that better than I. That's that problem.